I'll start my presentation. I'm Jubei Tada from Yamagata University, Japan. Our paper is entitled An Implementation of a Grid Square Code Generator on a RISC-V Processor. In recent years, statistical analysis which uses grid square codes has been focused. Although grid square codes are obtained from latitude and longitude based on several equations, this calculation requires a long computing time because it needs a lot of floating point instructions. In this paper, an execution unit which generates grid square codes from latitude and longitude is designed. The RISC-V processor with the proposed unit is implemented on FPGA and the performance is evaluated. At first, I will talk about grid square codes. Grid square codes are codes given when subdividing landscape into rectangular subregions by latitude and longitude. In this study, grid square codes based on JAS X0410 specified as Japanese industrial standards are used. The codes are expressed by numeric digits in which length corresponds to spatial resolution. Its notation is defined as PUQVRW. To convert degree notation of latitude and longitude to the corresponding grid square code, these equations are required. In 64-bit RISC-V processors, over 50 instructions are required to realize a function which generates grid square codes. Therefore, this paper proposes an execution unit which can generate the corresponding grid square code from latitude and longitude in one cycle. These figures show the structure of the proposed unit. The proposed unit generates the PUQVRW value from two single precision floating point values which illustrate latitude and longitude. The behavior of the proposed unit is as follows. At first, it is confirmed whether the input latitude and longitude are within an appropriate range. If latitude or longitude is out of range, the output value is set to 0. Next, P, Q, and R are generated by latitude. At first, exponent field is checked, and the temporary value is 1 bit left shifted or not. The mechanism to generate P, Q, and R is as follows. The value of P is the integer part of the temporary value times 1.5. This value is obtained by adding the temporary value and the 1 bit left shifted temporary value, and taking the upper 7 bits of the result. The value of Q is upper 3 bit of the remaining of the result. The remaining value after taking Q is multiplied by 10. This multiplication could be realized by adding the value and the 2-bit shifted value. The value of R is obtained by taking upper 4 bit of the result of this addition. As mentioned above, the hardware resources to generate P, Q, and R from the temporary value are only 2 adders. Next, U, V, and W are generated by longitude. The value of U is obtained by subtracting 100 from the upper 8 bit of the temporary value, and the other components are as the same as that of latitude. In this paper, the proposed unit is implemented on the ALU of RISC-V processor. The RISC-V processor, which implements the proposed unit, can generate the corresponding grid square code from latitude and longitude by 3 instructions. Now I will talk about the performance evaluation. We use Arien processor as a baseline processor. Arien is a 64-bit single-issue in-order RISC-V processor. Also, we use the Digiland Genesis 2 board for the implementation. The clock frequency when Arien is implemented on this board is 50 MHz. Xilinx Pivot Design Suite is used for designing. As a result of logic synthesis, the proposed unit uses 104 LUTs, and the maximum path delay is 6.956 nanoseconds. The maximum path delay of the proposal is 16.753 nanoseconds, while it is 16.307 nanoseconds for the baseline processor. As compared the proposal to the baseline processor, the number of LUTs is increased by 172, and the number of flip-flops is increased by 4. It is because that the instruction decoder becomes complicated for decoding a new instruction, and the multiplexer is needed for implementing the proposed unit on the ALU. To evaluate the performance of the proposed unit, the benchmark is executed on Linux, and the execution time is measured. As the benchmark, a program that counts the number of times randomly generated latitudes and longitudes match the specified grid square code is used. The number of iterations is 10 million, and the number of grid square codes the whole matching is 16. As compared to the baseline processor, the processor with the proposed unit achieves a 36.6% reduction of the execution time. Alien is an in-order single-issue processor. Therefore, it is considered that the effect of the proposed unit is enhanced. In order to evaluate the proposed unit in an out-of-order processor, the GEM5 simulator is used. As compared to the baseline, the proposal achieves a 23.9% reduction of the number of execution cycles. Although the performance improvement rate becomes smaller than the FPGA implementation, the effect of the proposed unit is still large. This paper implements an execution unit that generates grid square codes from latitude and longitude on a RISC-V processor and evaluates its performance. Experimental results show the in-order RISC-V processor with the proposed unit, which implemented on an FPGA, achieves a 36.6% reduction of execution time compared to the original processor. In future work, an accelerator which speeds up of the matching of grid square codes will be designed and evaluated. I would like to conclude my presentation. Thank you for your attention.